Everybody, just want to welcome you to week 9, module 9 for ME 144 heat transfer. So within this module here, we're going to wrap up our chapter 5 looking at transient conduction, and we're going to go through a couple different example problems together as well. Now, a couple bookkeeping items for this module here. You do have your quiz number 9. This has been posted to Blackboard, and it'll be due on Friday the 26th by 4 p.m. Also, you have your homework number 4. This will be assigned on Monday the 29th, and will be due on Monday, April 5th by the end of the day. So just a reminder, as always, I do have my office hours scheduled on Mondays from 9 a.m. till 10 a.m. If you're unable to meet during these times, please send me a message, an email, or a chat, and we'll find a time that works for both of us. Also, the TA has office hours on Mondays and Wednesdays. So there's 3 different sessions of office hours you guys have available to you. His office hours are from 11 to 12 a.m., and here's his email to contact him. This is a great opportunity with the TA to utilize his time for any homework-related questions or exam questions you have, as he is the one who'll be grading those. So let's take a look at our course schedule for the semester right now and see where we're at. We're down here in module 9 right now. So this week here, we're going to wrap up our chapter 5. So our first lecture is going to be dealing with sections 5.4 through 5.8. And then we'll be looking at 5.10 for our second lecture right there, where this lecture is going to be dealing with our spatial effects and the role of analytic solutions. And then the second lecture is going to be dealing with our finite difference equations right there. As you can note, there's our homework number 4 going to be assigned on this Monday, due on this Monday right here. So this is a few things that we want to take a look at as we're going through. We're coming down to the bottom here now. We can see we have our homework number 5, and this will be coming up within the beginning of module 13, due at the beginning of module 14 right there. And you'll see we'll be getting in here for our last 2 modules, 14 through 15, into our group projects. So keep thinking about your group projects. Those are coming up pretty quick as the semester starts to wrap up. So as we jump into our module 9 here, we're finishing up our chapter on transient conduction right here. And again, in particular, looking at our spatial effects and the role of analytical solutions in our module 9.1. And in module 9.2, we'll look at our finite difference equations. So within this whole module here, we're going to look at situations frequently where the Biot number is not small. So that right there means that we're going to have to deal with the fact that temperature gradients within a medium are no longer negligible. So we can't make this assumption anymore. So the use of lumped capacitance method would yield incorrect results. So everything we looked at before in the previous modules there using lumped capacitance won't work for this situation here. So we're going to need to take a look at some alternative approaches that we can use. We're also going to take a look at implicit and explicit forms of our finite difference solutions to transient conduction problems as we get into module 9.2. So objectives within this module, we're going to take a look at our spatial effects, talk about the plane wall with convection, look at the radial system with convection, talk about the semi-infinite solid, get into some objects with constant surface temperatures or surface heat flux, and then last we'll get into this finite difference method. So as this relates back to our textbook here, these are our reading guides down here as we wrap up chapter 5. So within Module 9, we're going to break this into 2 different sections, Module 9.1 and Module 9.2. For Module 9.1, we're taking a look at transient conduction, dealing with our spatial effects and the role of analytical solutions, in particular looking at some alternative approaches. So within this here, some of the objectives we'll be looking at here is our plane wall with symmetric convection conditions. We're looking at our Heisler charts, some radial systems, going over some semi-infinite solids approaches, and dealing with objects with constant surface temperatures or surface heat fluxes. So within this here, we'll go through the governing theories, take a look at some key equations, talk about some practical applications, and then go through some problem solving together. So now moving on to Module 9.2, we'll be dealing with transient conduction, looking at finite difference equations right here. So the thing we want to talk about now is the fact that analytical solutions to transient problems are restricted to simple geometries and boundary conditions, such as 1D cases that are considered in the preceding section. So these are really simple cases to really understand that theory, see how we apply our equations there. But even for some 2D and 3D simple ones, analytical solutions are still possible, even getting to some of the 2D and 3D geometries. We saw a little bit of that as well. But in reality, that's not always the case. In many cases, the geometry or boundary conditions preclude the use of these analytical techniques that we've talked about previously here, and we must identify some finite different methods in order to solve these right here. So in this module here, in the section Module 9.2, we're going to take a look at some of these explicit and implicit forms of the finite difference solutions for these transient conduction problems. So within this module here, we'll look at the finite difference method, talk about energy balance and the finite difference approximation for storage term, and we'll also look at the explicit and implicit method of solution right there. So this one here, we'll go over the theory of all these topics above, talk about our key equations, go through some practical applications, and then actually go through some problem solving together as well.